Hello, everyone. Yeah, the slides are working. Nice. So I'm Evelina Gabašová. I work in London in the Alan Turing Institute, which is the British National Institute for AI and Data Science. And first, I would like to talk a bit more about where I'm coming into this discussion from, so that you know you can trust me. You probably can't, but I'm part of the research engineering team, which is a team of people who exist somewhere in between the scientists and real-world applications. And I'm also a vice president of the Society of Research Software Engineering in the UK. And that's a non-profit organization that's trying to promote research software and the people who create it. And I'll be talking a little more about that. But first of all, our team comprises of people who have multiple different specialties. We have data scientists, we have software engineers, and we have research computing engineers. So those are the people who are trying to run things on a GPU cluster in the cloud. I am part of the leadership, so I don't get to program anymore very much, but I sort of exist in this space. And as I said, we exist somewhere in between what you would have in industry as software engineers and data scientists, and between academic researchers who are focusing on the science. And we care a lot about open source, and we care a lot about openness, because if something is important for academia, it should be making the research open and accessible to everyone. Yes, I just wanted to show a nice fancy slide that we had professional illustrators to make. But our team is sort of comprised of generalists we have people who are particle physicists, we have computational neurobiologists, we have cognitive scientists, we have a lot of people coming from all sorts of different backgrounds, being passionate about software and being passionate about doing things well. I don't want to talk too much about that. But I just wanted to give you a short example of 3 projects that I was personally involved in some way, or that came out of our team. And one is, this is an underground farm in a disused underground tunnel in London, where they were trying to grow microgreens. And it's really a controlled environment in a tunnel, where you can control the humidity, you can control some of the temperature, you can control how much fertilizer you give them. And we were working on creating a digital twin so that people can run simulations and assess what type of conditions give the best yield. Another example is this one from air traffic control. I was working on a project with the British Air Traffic Control Service. We didn't have anything in common with the issue that happened about a month ago, where all the planes were grounded and nothing could happen in the UK airspace. That's not us. But we are working with them to create an open platform for AI simulations, where AI agents can play air traffic controllers. And the last one, this is a machine loom from 18th century. And we are working with historians to look at various textual data from 18th, 19th century and modeling how the advent of machines influenced what's happening in literature. So that was a collaboration with the British Library. So we have a lot of different projects. Some of them are very computational, some of them are AI-focused, some of them are bridging areas that traditionally don't have a lot of computational component. But I wanted to talk about open source. So what is open source? The Open Source Initiative, OSI, gives a helpful definition. That's in 10 points. These are the headlines. It's like you have to have free redistribution, the source code needs to be available, it needs to allow derived works, and you can redistribute it, you can use it in any industry. It shouldn't discriminate people or endeavors. It should have a license, etc. I don't want to go through all the points. Who does any open source work? Quite a lot of people. Nice. So to summarize this, I think most of it is concentrating around transparency. The source code needs to be transparent, and how to use the code needs to be transparent. It needs to be reusable, and it needs to be extendable. You can extend it yourself. So for the purpose of this talk, these are the three main principles of open source. And I wanted to talk a bit about how this is reflected outside of software development in science. So open science, who has heard the term open science? Also quite a lot of people, nice. So open science is the idea that we should make the whole scientific process transparent and auditable, and we should publish all sorts of things, not just a paper at the end that some people can read. We should publish the data that we are using, we should publish how we are processing the data, we should publish what tools we are using to do that, and then the results at the end. But we should publish the whole pipeline, and that should be available. This is just from a handbook of open science where they look at various schools of thought why it's good to do open science. So it's good to depend on available tools. It's good to make sort of everything available. It's good selfishly because as a scientist you want to sort of be sure that you are not doing things wrong. So it's nice to have other people being able to audit that. I don't want to go through all of that. That's too much text. Overall, it's partly about democratizing access to science, to making the outputs available. And I wanted to talk about why. Why is this even happening? I have a couple of examples that are concentrated around my favorite topic in open science, which is spreadsheets. So, one example from the COVID. In the UK, they were big at contact tracing. And back in September, October 2020, they were constantly monitoring how many cases there are in the UK. And those are people who got tested and went into the system. And it looks great if you look at it. See, this is drop for weekend, and then it's mostly staying flat, meaning contact tracing must be working, everything is probably fine. And then they realized they were in some part of the process using an XLS format, which is the old Excel format that has a limit of 65,000 rows. They were getting data in a CSV file, putting them into Excel, and losing quite a lot of data because one test created multiple rows in the spreadsheet, meaning one file could handle only about 1,500 cases. So after correction, it looked like this. So they lost 16,000 cases of COVID. And that was at a time where they were calling everyone who tested positive and had them sort of input all the contacts they had over the past week, etc. So this was a major issue. And if you looked at the news articles around that time, they were having even interviews with people involved in this system, and they were saying that right now, yes, they are splitting data into multiple Excel files. Another example. This is quite an important paper in economics. It's so important that people refer to it just by the names of the authors. So this is the Reinhard-Rogoff paper. And it's talking about growth in a time of debt. And they did some analysis where they found or reported that countries that have high public debt experience lower growth. This came out back in 2010, and it was very influential in policy making at that time. And it was cited by politicians in their speeches. It was a very influential paper. Well, 3 years after that, these people published another paper where they are saying that they found coding errors, selective exclusion of available data, and unconventional weighting of the data. That's pretty horrible. And part of that came out of spreadsheets, where some of the data got omitted, probably. If it wasn't malicious, then it was through copy-paste error. And when you put in all the data and you process it properly, then all the effect disappears. So all the arguments against going into high public debt in an economic crisis were basically null. And another example, I did some work in computational biology. This is a paper from 2016 where they highlighted that there are gene name errors widespread in scientific literature. And those errors were that some of the genes are named in a way that when you put them into Excel, they are automatically translated into dates. So this is sept9, the gene is called septin9, and of course, it's the 9th of September. And there are a lot of them. So this is just the gene name, this is the internal Excel format, and this is the date it gets translated to. And they found, between the years 2015 and 2020, almost 40% of papers in Nature Communications had gene name errors caused by Excel. And that's not some rubbish publication journal. This is Nature Communications. And this is horrible, because anytime you want to take results of another paper and do something with them, they will have those errors in. And in the end, the result of all of this was that, I think 2 years ago, they published this paper, and this is a consortium of institutions that are dealing with genes. And they changed gene names. Excel was so horrible at dealing with gene names that they had to change the names of human genes. So, yeah. And another example, if you are not convinced that spreadsheets are evil in scientific work, this is another example. It's called Genomic Signatures to Guide the Use of Chemotherapeutics. And this was an exciting paper, because they found that if they just use a sample from a patient's biopsy, they take a few cells from a patient's tumor, and they look at it, look at gene expressions, how are genes behaving, and looking at how they behave in silico, in presence of various chemotherapeutics. Then they claim that they can choose which drug will work for which patient, basically. And that's huge, because the patient doesn't have to undergo sort of trials of different medications to see what will work. Turns out that they had a spreadsheet error. And their error was one-off, meaning they were transferring data from an Excel spreadsheet into another tool, and one of the formats was expecting a header and the other one wasn't. So this is pretty horrible. And when they actually fixed the one-off error, all the effects disappeared. And part of the reason why they didn't find it out before was because the results looked so good. And there were clinical trials started based on that. So it all boils down to something that we called reproducibility. And this is a sort of reproducible research framework, where if something is reproducible, it means that if you run it again using the same analysis on the same data, you will get the same results. If you run the same analysis on different data set, it will be replicable. If you run a different analysis with the same goal on the same data set, it will be robust. And if you run a different analysis on different data set, trying to model the same thing, and you get the same result, it's generalizable. But reproducibility itself, it's a very, very low bar. You literally run the same code on the same data. That should be doable, right? Not if you use Excel. So why is it hard? And where are we? This is all happening in the past 10, 15 years. And where are we? So there is quite a lot of push for reproducibility because obvious reasons. No one wants to deal with results that don't hold in practice. Well, right now, one prerequisite for actually being able to do things reproducibly is to actually do open science, because you need to publish all the steps that you took throughout your analysis workflow. So in the UK, they published this framework that is now being quite widely used, which is called FAIR. And you are supposed to publish data and software and tools in a way that's findable, accessible, interoperable, and reusable. So it all boils down to enabling reproducibility. Because to reproduce something, you need to find it. You need to be able to actually access it. It needs to work in reasonable conditions. And you are supposed to be able to rerun it yourself. So this all sounds really nice. And right now, we are in a fairly exciting stage where we do non-paper publications. We publish things in JOSS, the Journal of Open Source Software. You put things into repositories. You can put in data. You can put in benchmarks. You can put in standards. And research software engineering, which is where I work, is part of this movement, because you don't want biologists and people generally not trained in computation or in software to do all the software work, because that's necessarily not going to be reproducible. So there is now a whole profession of people focusing on doing proper research software. And this is just a bunch of acronyms that's related to the funding system in the UK and in Europe. And there is now a push to acknowledge people who are not academics, that are contributing to the scientific ecosystem. And Rev 28 is sort of another round of UK university evaluation, and now it can include software, and people who are not academics can submit things, and it can be anything, like an open source package. And it's getting quite a lot of community recognition. There is now quite a huge community in the UK. Let's talk about something different. So I want to tell you a story about my most impactful work. So 7, 8 years ago, The Force Awakens was coming up, and I signed up to do a blog post before Christmas as a part of the F# Advent calendar, which was a community activity where people signed up to publish a blog post on the day during Advent. And everyone was talking about Star Wars, at least within my community. And I thought, what can I do with Star Wars? And then I found out that you can download the scripts of all the movies that came out. So this is an example of a script. It starts with int or ext, meaning interior or exterior. Then there is a description of how the scene looks like. And then you have the name of the person speaking and then what they are saying. And I thought, OK, I can do this. I can parse the scripts, and I can create a social network of Star Wars characters that if they speak together in a scene, that means they met and they have some kind of relationship in the movies, and I can create a social network out of that. That's easy, right? Well, a couple of horrible regular expressions later, I was able to parse everything. If you ever wondered how the names of Star Wars characters look like, this is the regular expression that matches all of them. They are quite horrible. Because they can have like not just letters, but numbers and weird characters. So this is a Star Wars social network, how it looks like, and it's quite nice because you can see that here it concentrates on the original trilogy, and these are the prequels, and some of the characters are sort of in between. And I believe this is my most impactful work academically. Thank you. Let me explain. Okay, no, let me explain. The thing is that I put this on GitHub and forgot about it. And I kept getting emails for ages later. People use it as an example data set when they are doing social network modeling. And it made its way into a textbook. People are using it in talks. I got an email from someone doing research on social networks in sharks. And they said that they are using my data set as an example data set. So I just wanted to say that not everything gets captured by these impact frameworks. And sometimes the things that have the most impact are the things you would least expect. And let me talk about open source. I was talking about open science, but let me talk a bit about open source in the academic ecosystem. I was reading this book. It's called Working in Public, The Making and Maintenance of Open Source Software by Nadia Ekbal. And she has this very nice overview of how open source software gets created based on the number of users and number of contributors. And I will go through that. And by the way, it's a fairly nice book outlining how the open source ecosystem looks right now. So, first of all, well, the user growth is always sort of much larger than contributor growth. But if we have a lot of users and a lot of contributors, it's called a federation. And that's the sort of type of open source that you probably most frequently think about. It's a large distributed network of people contributing to something. So, for example, things like Linux and things like Rust. Rust is supposed to be a federation as well. Then if we have a lot of users, but a small number of contributors, it's called a stadium, because there is just a few contributors, few creators, and a lot of people, a large user base. An example is a lot of projects in the JavaScript ecosystem, for example, Babel, which has very few people actually doing the work. Babel is the JavaScript transpiler, and it gets used by a lot of people. And then if the user growth is small, but the contributor growth is large, that's called a club. That's usually happening in smaller communities and around various niche programming language. I've been a part of the F# community, and quite a lot of projects there are clubs where basically the people who use it are also contributing, and yeah, various hobbies and smaller programming languages. And the last one, when the user growth is small and the contributor growth is small, it's called a toy. So let's do a quick poll. Who ever contributed to a federation? Couple of people, nice. Stadium. Oh, more people, interesting. Club. More people. And a toy. So I did a similar poll at a research software engineering conference last week, and the vast majority of people raised their hands for toys, because I believe that the current academia is mostly creating toys. And it's not a bad thing. It's not a bad thing per se, because the researchers get to play with them, but then they get archived on GitHub. But GitHub is not an archival tool, right? So it more or less looks like this. It looks like a pile of abandoned, discarded toys. And GitHub is a social network. I was going to the US, and I had to fill in handles from my social networks, and they asked for GitHub specifically, because they consider GitHub a social network. So in reality, GitHub is where academic open source goes to die. There are exceptions, of course. All of these projects came out of the academic environment, and they did succeed. Another example is SK Time, which there will be a workshop, I believe, over the weekend that came out of the Alan Turing Institute originally as well, and it's trying to model time series in the spirit of scikit-learn. But of course, the elephant in the room when you are talking about open source is funding. Open source struggles in the normal business world. It struggles in academia as well, because people want to be able to point at a deliverable that they will do for a project, and maintaining an open source package is not something that would count. The only sort of viable model in an academic ecosystem is to do a club. And some examples of clubs are things like AstroPy, which is astrophysics-focused Python package, where it's easy for the community to contribute because they are also the users, and it's very, very specialized. And another example is the Turing Way. Some of the images that I was showing came out of the Turing Way, where it's a community-driven handbook for reproducible science. So it's actually incredibly hard to get something done. And I was getting a signal that I should speed up. So I will skip a few slides. If you want to talk about this, I do have a lot of opinions. So find me later. Okay. Let's talk about another topic that I am passionate about, which is open source AI and open AI. Please notice that there is a space between open and AI. This is not about the company OpenAI. That's not open. And why is this interesting? Who uses ChatGPT? Who uses Copilot? A lot of people. So large language models are the most exciting thing that happened in AI in some time. And quite a lot of companies publish their models, or individuals publish their models. But the thing is, that's not all that goes into an AI system like this. There's a lot more. If you want to see how anything was done, you need to have not just the weights of the model. You need to have the source code that was how the model actually looks like, what training data was used, what editorial decisions were made throughout the training. And the largest one and the most complicated one is infrastructure. Because if Google publishes how they created BART as their large language model, even if they published all the source code, there are maybe 3 other companies that would actually run it, because we don't have the Google scale infrastructure. And this is the generative AI landscape in terms of openness, where on one hand you have just internal models that no information is available about, but they are used in products internally, like Palm 2, which is a Google model. Then you have models that are available only as a hosted access, like Midjourney, which you access through Discord. GPT-4, Claude, these are the ones where you have API access. Then you have some that are downloadable. You can download the model weights, but basically nothing is known about those. And ultimately, there are initiatives to create large language models that will be completely open, where all the training process will be transparent. And that's, for example, Bloom, which was a community large language model created by a consortium called Big Science, where Hugging Face was taking quite a lot of responsibility. But when you are publishing something, when you are publishing software, this is a website from Google, which license. It's very simple, right? They are basically giving you 3 rules. Either pick the license that's the most used in your community, or use the MIT license, or if you care about sharing the improvements, use the GPL. That's simple, right? You know how it looks like in AI right now for models? These are some examples. So GPT-2 came out 4 years ago, and it was published under the MIT license. Is it appropriate? It's a license for software. It's not a license for training models. The YOLO model, which is you only look once, which is for real-time object detection, uses the YOLO license, which the text of the license is, this is sort of available publicly. Don't email me about it. Do whatever you want with it. Then Bloom was published under the Rail license, which is Responsible AI license, which tells you you can use it for anything, but don't use it for misinformation, harming the humanity. It's very vague, but don't use it non-ethically. Yeah, now, last week, there was this Phi model, which is a fairly small large language model that's trained not on all the rubbish from internet, but on a curated set of documents, so it doesn't actually give you all the nasty comments and everything. And that one is published under Microsoft Research license, which tells you, yeah, you can reuse it, but you can't actually run any production system. And Llama 2 came out of Meta, Facebook. And the license is, you can do, it's basically an open source license with one point that says, if the number of monthly active users is greater than 700 million, you have to ask them for a license. What kind of, this is not an open source license, of course, because it's limiting how to use that. But this is a Wild West. People are just choosing whatever they think might be doable. And OSI's reaction is that they are right now running a process to define what open source AI actually means. Because all of these companies are publishing things and claiming this is open source, but it is not. And it certainly doesn't have that democratizing access feature which normal open source has, because you don't have the infrastructure to run most of these things. And what's interesting is, I don't know if you have seen this note that leaked back in May, where someone from Google in an internal conversation was saying that basically open source AI will win and they don't have any mode, we don't have any way to stop that. And Meta is embracing that. They are publishing their large language models, namely the Llama family of models. And they are basically using open source to own the ecosystem, because once they publish their large language models, because they are very capable, all the open source efforts were centered around those models, because people will be using them. They are the most powerful. So there's an interesting power play happening right now, and Meta has been successful in putting PyTorch into the community, and it gets used quite a lot. And they are replicating that now in the large language model space. If you want to learn more about it, read this paper. It's quite a damning view at the political power that all of these companies have, and how does that get reflected in the open source communication. So just to wrap up a little, as I said, the open source principles that I wanted to talk about were transparency, reusability, and extensibility. In open science, in academic open source, the focus is very much on transparency because reproducibility is an issue. So you need transparency and you need reusability. The extensibility is not such a big thing. For some reason, academics are very, very wary about using other people's stuff, so they want to implement everything from scratch themselves. And in open source AI, it's very much focusing on reusability and extensibility. All these companies, they don't really care that much about transparency. OpenAI is claiming that they can't release GPT-4 into the world because it's too dangerous. So they are not publishing even any information about what it was trained on, how it was trained. But they are allowing API access. So in terms of open source, look at what the motivations are. Sometimes they focus on only some of the aspects of the whole open source landscape. And that's my last slide, so thank you.
Thank you very much, Evelina. And we do have some questions on Slido. First one is about a very important topic. Did your research shed any light on whether Jar Jar was a Sith Lord?
Unfortunately, it didn't, but it wasn't the main focus. So maybe we could find some arguments for that to be true.
So further research needed?
Well, the data set is openly available. Go download it.
Do we have any questions from the audience in the meantime? Just raise your hand. Oh.
Thank you so much. Well, first of all, thank you very much for the conference. It was absolutely amazing. And I have one question with regards to the latter of your conference. So you highlighted, let's say, some dangers of AI, like ChatGPT-4 refusing to give full access, but still they give access to their API. Now, as being part in the open science, do you think that we should devote more effort as to how to prevent the dangerous uses of AI before we even try to push for open source AI?
I think that's a very good question. Can we prevent dangerous uses of AI? I think the genie is out of the bottle now. There are many openly available large models that are not as capable as GPT-4, but very, very close to that. The Llama model from Meta is basically on the same level. It was trained on the same scale of data. So I don't think we can do a lot right now because it's published. People are using that. And personally, I believe that the more we actually teach people about large language models, the less hype there will be, hopefully. Because right now it's a gold rush, and it's hard to see what's a marketing claim and what's real. And in terms of OpenAI talking about ChatGPT being too dangerous, it's partly a marketing claim. And ultimately, it's just a model that predicts a next word or next token. And we've had those for a long time that were less capable. Now they are more capable, and they are. We will have to find what the good uses are, but yeah, don't trust anything on the internet right now. Sorry, that's a bit bleak, but I think this is a very messy landscape, and I just wanted to highlight that there is a culture war happening right now, where there is quite a lot of open effort. For example, the Bloom model, which was community-driven or a large consortium of different institutions and people, and that is trying to be as open as possible. And on the other side, there are big companies that are trying to put their models out there and own the ecosystem.
Are we doomed to use Excel in research? What are the alternatives?
Don't use Excel in research. load your data into Pandas or whatever you are using and use that. But the bad thing is that if you collaborate with anyone who has to use Excel, then yeah, teach them Python. Sorry. Just a small anecdote, I was sitting next to a PhD student years ago, and he was creating heat maps in Excel. Heat maps. I didn't even know it was possible. And I was telling him, come on, R is installed on the machine you are using. I will teach you how to do it in R, because that's literally 2 lines of code. 1 to load the data in, and a second to visualize it in ggplot. It's easy, I will show you. And he was like, well, let me just finish those 4 last heat maps and then I can learn. It's hard.
And that's all the time we have. Thank you, Evelina.